So we did an example yesterday of the rational zeros theorem, but then we got to, I think, this slide here, and we ran out of time when we were coming up with the P over Q values. I think we eventually got all of them, okay? But then the bell rang, and we didn't know, we couldn't do anything else with it. Okay, so I want to come back up with those P over Qs, just remind you how you find those. Remember, this is your A sub 0, and this is your A sub n. Okay, those are your coefficients. That's what we call those, constants and coefficients. P is the factors of A sub 0. P equals factors of A sub 0. Okay, and Q are factors of A sub n. Okay. Now what happens with this stuff is that the bigger A sub 0 is, and the bigger that Q is, or sorry, A sub n is, the larger the group P becomes, and the larger the group Q becomes. Okay, which can be problematic. If I have, you know, if that 6 was 36, 36 has a lot of factors, right? Okay, I got a lot of P values. If that 2 was like 8, 8 has a lot of factors. Okay, I get a very, very, very large list of P over Qs. Okay, which is fine. It's just in the event of trying to figure out which ones work, that's where it becomes a problem for us. Okay, but developing the list in itself is not all that terrible. Okay, so when I find these values of P, it's just the factors of these. Okay, and it's always the plus or minus. Okay, so I'm going to go plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, right? Those are the factors of P. I keep saying that wrong. Those are the factors of A sub 0, which known as a group, we call them or reference them as P. And the factors of A sub n are the factors of 2 here, which we call the group Q. Okay, those are plus or minus 1, plus or minus 2, right? All we have to do then, once we get those two lists, all we have to do is develop a list of P over Q. Okay? Now P over Q is equal to the possible zeros, call them real zeros, of P of X. Okay? Meaning that all zeros will be of the form P divided by Q. Okay? When we get done with factoring one of these things, okay, and using basically the rational zeros theorem a few times, but then ultimately, hopefully, getting down to being able to use the quadratic formula or our completing the square or factor by grouping techniques, whatever, we'll be able to factor pretty much any polynomial that we want to. And when we get our final solution, okay, breaking P of X all the way down to all of its linear factors, if there are real zeros, those real zeros will all be of the form of P divided by Q. Okay? So let's find those values of P over Q. There's like a button down here that I want that should say extend page, but that slider won't stay on. Alright, so our P over Q's. What you're going to do is you're going to take every P value and divide it by every single Q value. So, I'm going to start with that P value, okay, and divide it by both of these. So plus or minus 1 divided by plus or minus 1, and then plus or minus 1 divided by plus or minus 2. Okay? Now you don't need both sets of plus or minuses. Okay? You got plus or minus 1 over plus or minus 2, and you start comparing all those pluses and minuses, you're going to get either plus or minus 1/2, or so plus 1/2 or minus 1/2. Okay. The next thing you're going to do is the exact same thing for that 2. Okay, so we go plus or minus 2 over the first q of 1, and then plus or minus 2 over the second q of 2. Then you're going to do the same thing for that p-value of 3. So plus or minus 3 over 1, plus or minus 3 over 2. And then your last p-value is -6. So you'll do the same thing. You go plus or minus -6. Sorry, just plus or minus 6 over 1, and plus or minus 6 over 2. And those are all your potential zeros. So when we factor this and we get it all the way down to its linear terms, if there are x-intercepts, okay, if there are zeros, okay, then they're going to be at plus or minus 1, plus or minus 1/2, plus or minus 2, plus or minus 3, plus or minus 1.5, plus or minus 6. Okay, those are the only places that they could occur. Does that make sense? Okay. Now it's not saying that they're going to occur there. Okay, because we could have maybe a 4th degree polynomial, or even a 2nd degree polynomial, anything that's even. We could have a graph like that, right? And zeros are where the graph crosses the x-axis, right? That one doesn't, right? Okay, so that one would have a bunch of imaginary factors, okay? Things like a plus bi, all right? We'll learn how to do that kind of stuff later on. But this theorem is showing us that if this thing does cross the x-axis, it's going to do it at one of those 12 spots, okay? Or a grouping of those 12 spots. Now there's a couple in here that are redundant. 2 over 2, same thing as 1, right? So I'm not going to do that one. And then 6 over 2, same thing as 3. So you can kind of cut your list down a little bit that way. Okay. Now, obviously, you start to see that when we deal with this process, the more factors that P has and the more factors that Q has, that list becomes very large. Okay, and that becomes problematic for us by doing this by hand. But we'll do some of these by hand, but then eventually we'll use some technology to cheat a little bit. Because if we've got it at our disposal, we might as well use it as long as it's going to benefit us. And I think we'll. So what we do once we find these P over Qs is that we're going to go through synthetic division. We're going to go 2, 1, -13, and 6. Okay? And we're going to go through synthetic division using those P over Qs in our box. Because these are potential zeros, so we're going to put those in that box and go through synthetic division and hopefully figure out a remainder of 0 for some of them. Okay? Now, what happens right now, we don't have a good idea of what one of those P over Qs to start with, right? Okay? Our technology, when we start using that, will give us a better way of starting at one of these values. We have 2 rules, one called Descartes' rule of signs, which basically by looking at the plus, minus, and the plus in the original polynomial, we could determine maybe which ones to look at, which P over Qs to deal with first. And there's another one called the lower and upper bound theorem, which basically says if we look at a remainder line and if it's always positive or has a, alternates positive to negative, maybe we can cancel out some values out of our P over Q, and it just kind of maybe focuses our attention on a group of P over Qs instead of the whole list. Does that kind of make sense? And we'll get to talk about one of those hopefully at the end of the period, but maybe not the other one until Monday. But right now, the only thing we can do is just start choosing maybe the first one. So I'm going to put 1 in there. Okay? And I'm going to go through and I'm going to try to do synthetic division with this. Just put my 2, 2, 3, 3, -10, -10, remainder of negative 4, right? So I'm looking for a 0 there where that negative 4 showed up, right? Okay. So this tells me, because I got a negative 4, that positive 1 is not a 0, right? Positive 1 is not a 0. So I'm going to start over. I'm going to do the entire synthetic division again, but I'm going to go to the next P over Q option. And my next P over Q option is negative 1, right? Now I know for you guys that this is going to be kind of cruddy because you can't do that very easily, right? Okay, so you kind of probably have to go down on your page a little bit, create another synthetic division with that line of numbers, and go through it. If you want to erase, you can erase, but I think you start erasing the same spot over and over and over again, you put a hole in your paper. I bring that 2 down, because we might go through 5, 6 of these numbers before we find our first 0, right? Okay, our first 0 might not be until we see 6. Okay, maybe 6 is a multiplicity of 3 or something like that, and that's the only 0 that we get. So we would do a lot of work, kind of disproving that that's a 0, that's a 0, that's a 0. Does that make sense? Okay, so, and we just don't know. But negative 1 times 2 gives me negative 2. Add those down, you get what? Negative 1. Multiply those together, I get 1. This gives me negative 12. And then that gives me, obviously I'm not going to do the net, because this is something you guys can kind of visualize. You can do that little foreshadowing. If I multiply those together, I'm going to get 12, right? 12, a positive number plus another positive number is not going to get me to 0 yet, right? And the more you do these, the better you get at it. You can maybe, I could have probably stopped there and kind of foreshadowed. These numbers are not going to align themselves enough to give me a 0 over here. So, negative 1 does not work. So, what do we do? Those 2 are done. We're going to go to the next option, 1/2. Bring my 2 down. Gives me 1 there. Bring my 2 down. Gives me 1 there. Gives me negative 12. Now negative 12 times 1/2 gives me negative 6. And it tells me I've got a 0. Okay? So that's nice that we only had to do two synthetic divisions before we got our first 0. Okay? Now what is really, really nice about this is that understanding what you started with, that was x cubed, right? This was x minus 1/2 out here, right? Taking cubic, dividing it by a linear term is going to make this go to a what? X squared. Okay. Now, if you start with a cubic and you find 1 0, you are basically done with your synthetic division because your depreciated quotient here is now of a quadratic format, and you have better ways of factoring that than the rational root theorem. Does that make sense? Okay. You can use your A times C method. You can use factor by grouping, or which is basically the A times C method. Or you can use your product and sum stuff. You got better. You can use quadratic formula. You have better techniques to factor that quadratic in the rational root theorem. If you had something to the 4th power, okay, if P of x started off being a 4th power polynomial, you would want to find 2 zeros using synthetic division before you could use a quadratic formula or using other quadratic factoring techniques. Does that make sense? Okay. But now that I've got that format, 2x, this is 2x squared plus 2x minus 12. Okay. I'm just going to write it that way right now. This is x minus 1/2, right? If I multiply those out, that is how I factored P of x so far. Okay. Whether you want to write that now or just continue with the factoring of 2x squared plus 2x minus 12, that's fine. I think a lot of times people will go through this work here. They will factor everything that they need to, but then at the end, they kind of lose sight of what they were doing and what all these factors kind of tell them. So I like to, every once in a while, once I find a 0, I like to, and a factor that goes with that, I like to write down what my new polynomial looks like. Okay, I factored my polynomial, now I'm down to a linear term and a quadratic term. We know quadratic terms can be factored a little bit further. So I'm going to take this. What's the greatest common factor in there? 2. So I'll bring that 2 out. And that leaves you then x squared plus x minus 6, right? Okay. So how does that quadratic factor then? X plus 3, x minus 2. Good. The one thing you got to realize is that when you bring that GCF out, when you bring that 2 out, it does not disappear, right? Okay? It would only disappear in the event that we had an equation where 0 was over here and we're dividing both sides by that 2. Okay? Then it would disappear, but in this case, because we're just altering the way something looks, we can't let it disappear. Okay? My x minus 1/2 is my other factor, right? Now I've taken p of x, and there's a linear factor, there's a linear factor, there's a linear factor. Okay? So I've taken my p of x and I've factored it down to all of its linear factors. The reason we want to do that is because our linear factors tell us what? Yeah, it tells me my zeros. It tells me where I cross the x-axis. So now I've taken the polynomial, I found its zeros, okay? I know that it's a third-degree polynomial, so I know it's in behavior. I can use the information at the beginning, the original p of x, to find the y-intercept, and I can start getting a pretty concrete, comprehensive graph by doing that, okay? When we look at it this way, I like to keep this 2 out, okay? But there's nothing wrong with multiplying it through one of your factors. You can't understand that this is a number, that's a number, that's a number, and that's a number once we know x, right? So when I want to, so I got 4 numbers being multiplied together there. If I want to put that 2 somewhere else, I want to multiply it through something, you can only multiply it through one of these binomials, right? I see a lot of people try to distribute that 2 to everything. You can't do that, but you can pair those two up. I think that's probably the most logical thing to do here. And rewrite this as 2x minus 1 over at, or times x plus 3 times x minus 2. Those say the same thing. I don't like the bottom one because when I try to find zeros, don't I have to do a little bit of work with that 2x minus 1 to find a 0? Yeah, okay. So I think the top one's a little bit better, but it doesn't really matter how you write that. But what I do want you guys to understand, look at those zeros. The 0 of 1/2, the 0 of -3, and the 0 of 2, right? 1/2, we'll run over here, 1/2, -3, and 2. Those were my zeros. And if you remember, P over Q said when you are done, when you factor your polynomial, and there are real zeros, they should be of the form of P over Q. So let's go over to our P over Q list. Are those numbers? Is 1/2 one of those? Is -3 one of those? And is 2 one of those? Yeah. You will never have a 0 that is outside that list. Okay? So, you know, if I developed a list of P over Q just like that, okay, I should never factor something and get like 7/2 back, because 7/2 is not in that list of P over Q. That makes sense, everyone? Now, what becomes problematic, like I said earlier, is when this number becomes larger, okay, more factors, has more factors, and when 2 has more factors, this leading term here, that list gets pretty ugly pretty quick. Okay, so we got some tools that people before us have found to be very useful and true. So let's talk about this. Where are they at? There we go. One of the most influential mathematicians in regards to our algebra is a guy named René Descartes. Okay, French guy, but he's the guy that came up with the Cartesian plane, which we call the XY axis, right? Okay, so that linked the geometry concepts ultimately to algebraic concepts. A couple other influential mathematicians, probably the top 3 mathematicians, maybe top 4 that we talk about, we use in algebra are Descartes, a guy named Frederick Gauss, Newton, Sir Isaac Newton, and who's the other one? Leonard Euler. Okay, those are some of your most influential math people. There's a lot of theorems and rules and properties that are attributed to those people's names. Okay, so Descartes' rule sign contributed him. Basically, what it is now, there's some legwork necessary prior to doing the factoring here to get an idea of what our zeros are going to look like. Okay, so you might think, well, this is a lot of extra work. But in comparison to having a list of P over Q, let's say that Q has 5 factors and P has 12 factors. That'd be a list of 60 P over Qs, right? And if they're plus or minus, that's a list of 120 P over Qs. Okay? You don't want to be able to have to go through every one of those, right? So even though there's some work involved in determining the usage of Descartes' rule of signs, it is much less work than checking every P over Q. Okay? But what he says is he talks about a variation in sign, okay? Or a sign change, okay? And what you do is you look at successive terms, okay? And you look to see, did a change in sign occur? So in that first one, we go from 5x to the 7th, a positive, to a negative 3x to the 5th, right? So that's a variation or a change in sign. So we count that, okay? We go from a negative 3, and so then we go to the next one. So negative 3 to a negative 1, right? Okay? Well, negative 3, negative 1, that is not variation. That stayed the same, so we don't count that. Then we go negative 1x to the 4th, and a positive 2x squared, right? So we went from negative to positive, so we count that one. So we're up to 2 sign changes so far. Then we're at positive 2x squared, positive x, no sign change, so you don't count it. Then we go positive x to negative 3, there's a sign change, so we count it. So that one would have 3 sign changes. Does that make sense? Or 3 variations in sign. Okay. I'm going to write that P of x over here real quick. So I don't want to have to. We're going to jump back and forth in a moment. So 5x to the 7th minus 3x to the 5th minus x to the 4th plus 2x squared plus x minus 3. Okay. So we just found out that there is a variation of 3 in regards to signs there. What his rule says, okay, so now we know what sign variation means. What his rule says, it's 2 components, 2 parts. But it says, let P be a polynomial with real coefficients. It says the number of positive real zeros, okay? So what that means to us right away is that now we're looking at our P over Qs that are positive, okay? The number that we're going to have of those in our final factored polynomial is going to be either equal to the number of variations in sign, or it's going to be less than by an even whole number. Okay? So, think about this. This is P of x, right? We had 3 sign variations, right? Okay? What that number 1 statement says in his rule is that your polynomial, when you factor it, is going to have 3 positive zeros, or that many remove an even whole number. Okay? So what's the even whole number that I can remove from 3? 2. So what his rule here says is that you're going to have 3 positive zeros or 1 positive zero. Kind of make sense? Okay? So as we're going through maybe our list of 120 P over Qs, and I find 3 positive ones, could I say I'm done looking at all positive P over Qs? And I just cut my list in half of what I have to look at as I continue to factor that polynomial. Does that make sense, everyone? Okay? So that's nice. Okay? But the second component says, okay, this is how you would deal with negative negative zeros, okay? To do negative zeros, so this was positive zeros. Okay, to do negative zeros, you got to do, again, a little legwork. And what his rule of sign says is that it's basically the exact same thing, but instead of for P of x, we have to look at P of opposite of x. So what we need to do here is take this original polynomial, and evaluate it for negative x. So I'm going to go 5, negative x to the 7th, minus 3, negative x to the 5th, minus negative x to the 4th, plus 2, negative x squared, plus negative x minus 3. So I write that out, just using what we've talked about in chapter 2 about how we evaluate functions at different values. Okay, in this case a variable value. But now I evaluate that. Well, negative 1 to the 7th power is negative, right? So it's going to become negative 5x to the 7th. This is going to be negative x to the 5th, but I got a negative out here, so it becomes positive 3x to the 5th. This is going to be negative x to the 4th, becomes x to the 4th, right? But it's negative here, so total is negative x to the 4th. That's going to become positive when I square it. That's positive, so positive x squared. That'll be negative, and then minus 3. So there's p of negative x. So now I'm going to go through and look at sign changes. Is there a sign change between those two? Negative and positive, right? Is there a sign change between those two? Positive to negative. There's a negative to a positive. There's a positive to a negative. And then negative to negative, right? So how many sign changes do we have here? 1, 2, 3, 4, right? Okay. So what his second statement there says the number of negative real zeros of p of x is either equal to the number of variations in sign p of negative x. So right now, that first statement, we get the idea that we have 4 sign changes. So that is going to provide us then 4 negative zeros. Or, okay, so that's what the first statement is. Either is equal to the number of variations, 4 for us, or is less than that by an even whole number. So less than that by an even whole number, what would be less than this by an even whole number? 2 or 0. Okay? So basically when it says even whole number, that's just a quick way of saying take your number of sign changes and continually start subtracting 2 from it until you get down to either a 0 or a negative number. Okay? And then you stop. Okay? So right now we know that we have this potential 3 positive zeros or 1 positive 0. And now here we have either 4 negative zeros, 2 negative zeros, or 0 negative zeros. Okay? Now thinking about your 7th degree here, okay, and I start finding maybe some of these zeros, you can start to eliminate the possibility. If I find 2 positive zeros, I automatically know there's going to be a 3rd positive 0, right? Okay. And then if I find 3 positive zeros, doesn't that mean that I'm going to have 4 negative zeros? Okay. Or, I guess maybe not 4 negative zeros, but I might have 2 negative zeros that have multiplicity of 2. Is that going to make sense? So there's a lot of things kind of interweaving itself to give you an idea of which P over Q's to look at. Okay. There's another theorem. I'll kind of give you a rundown of it real quick. Going back to what we did here. Okay. Let's just look at our P over Q values right there. What we call the upper and lower bound theorems basically says once we do synthetic division, maybe I started synthetic division with a 2 here. Okay. Basically what it says, if you look at your last line of remainders, your last line of synthetic division, and it has a certain relationship. We'll talk about that relationship on Monday. But if that relationship holds, it might tell you that's not a 0, but it might also tell you those are not zeros as well. Does that kind of make sense? Okay, so it just cut your list basically in half, right? And then maybe I try maybe 3 halves, and I find out that that's not a 0, but my last line might tell me it also means if that's not a 0, then that one is not a 0 as well. And then did that narrow my view down to a very small section of P over Q's? Yeah, okay. And that's called the upper and lower bound theorems. But those are 2 things that maybe in a pre-calculus course you talk about. I'm going to be perfectly honest with you. I've done a lot of math in my life. Okay, probably more math than a lot of you will in the rest of your lives, right? Guess how many times I've really used the Descartes rule of signs and the bound theorems. Just when I teach it, okay? And when I do my math homework, stuff like that, I never have to use this, okay? Because we have technology that's going to help us kind of get the ball rolling to begin with, all right? So we'll talk about that on Monday. But I do want you to understand that there are techniques out there, there are algorithms out there when a procedure is very arduous, very technical, and takes a long time. There's often theorems that allow us to alleviate some of that work. Okay, this is a perfect situation out there.